comprehensive exam, right? So you have to have all the sections. So I'll give one question from each sector. Okay. Like first 5 and 4 and 5, I'll give one question. And then chapter 7, 8, 9, I'll give 2 questions. Okay. 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 So yeah, so let's start the presentations. Today, first group is group 4. Okay, so group 4, please.
Hello everyone, we are group 4. I'm Pauline. Today we present FM modulation and demodulation principles and Simulink simulation. Our presentation includes 5 parts. First, FM modulation principles. Second, FM demodulation principles. Third, Simulink simulation of FM modulation. Fourth, Simulink simulation of FM demodulation. Fifth, summary. First, the part 1, FM modulation principles. The definition of FM. FM is a method of covering information by varying the frequency of a carrier wave in proportion to the amplitude of the baseband signal. The advantages of FM. FM offers superior noise immunity and high fidelity audio transmission, making it ideal for broadcasting and communication applications. And the principle is clear. The baseband signal passes through a integrator. then enters the phase modulation together with the carrier signal. The baseband signal controls the carrier frequency, while the carrier amplitude remains constant. Information is carried by frequency changes. Now is the part 2, FM demodulation principles. The definition of demodulation. FM demodulation is a process of extracting the original baseband signal from the reduced FM modulated signal. The importance of demodulation. Accurate demodulation is crucial for covering the transmitted information without distortion or loss. We use the phase-located loop for demodulation. A PLL includes 3 core parts: phase detector, low-pass filter, and voltage-controlled oscillator. It covers the signal, separates low and high frequencies, laters our high frequencies, and looks at the phase to recover the baseband signal. And my part is over. Next is my member.
The purpose of simulation is used to visualize my name is Willow. And analyze the FM modulation process, providing insight into the behavior of the modulated signal and the impact of various parameters. Simulation environment. The simulation is performed using MATLAB and Simulink, a powerful tool for modeling and simulating dynamic systems. Baseband signal. And this is the question. In the simulation, the baseband signal is integrated to control the carrier phase and generate the FM waveform. We can observe the baseband signal integrated phase deviation, instantaneous frequency, and the typical sideband spectrum of FM. The results match theory well and verify the modulation principle. That's all for part 1, 2, and 3.
I'm Cindy 心仪照。Thank you. Now part 4. Simulation of FM demodulation. We built a PLL demodulation model in Simulink. We use the matrix multiply block as the phase detector, analog filter design as the low-pass filter, and the continuous time VCO as the oscillator. The simulation shows the system can stably track frequency changes and accurately recover the baseband signal. The demodulated signal has a smooth envelope and low distortion, proving reliable performance of PLL demodulation. Finally, it's a brief summary. First, FM modulation adjusts carrier frequency via baseband signals. It features high fidelity and good noise resistance. Second, PLL-based FM modulation can accurately restore original signals with stable performance. Second, our Simulink simulations fully verify the modulation and demodulation theories, combining theory with practical simulation results. That's all of our presentation. Thank you. In conclusion, the principles of FM modulation and demodulation have been thoroughly explained, and the Simulink simulation have provided valuable insights into the practical implementation and performance of these techniques. Thank you for listening.
and we choose project 2. And in this presentation, we will introduce 2 ways to realize SFB amplitude modulation with MATLAB. And the 2 ways are the MATLAB script and the component of MATLAB, that is Simulink.
Yes, let me introduce the first part, the MATLAB code with basic parameters. This part, our goal is to generate an SSB signal and verify that it works by looking at its frequency spectrum. So why do we want the SSB? Because traditional AM modulation transmits 2 identical symmetrical sidebands, one on the left and one on the right. This actually wastes half of the bandwidth By using the phase shift method, we can literally chop off one unwanted sideband and keep only the other half. So this saves half of the frequency space and makes our transmission much more efficient. Next is the co-equation in this middle. This equation, the first one, ST equals cosine 2 pi FCT is our original method signal multiplied by a cosine carrier. This is exactly how standard modulation works. The next part is the ST sine 2 pi FCT. This is where the magic happens. This ST pronounced as hat is the original signal after passing through a Hilbert transform. Think of the Hilbert transform as a universal phase shifter. It takes every single frequency component in our original signal and shifts its phase backward by 90 degrees. We then multiply this phase shifted signal by a sine carrier. In this step, we will take the multi-tone method signal FT so that we defined in the previous slide. That one made of the with the 500 hertz, and the second one with 1000 hertz. The third one with 1500 hertz. In our code, we will use the built-in Hilbert function to get our 90 degree phase shifted with just one line of the code. Yes, this is my part to introduce the basic parameters to you. So I will introduce the second part.
Hello, everyone. Next, the second part, I will briefly introduce our MATLAB implementation of multi-tone baseband signal generation and Hilbert transform. First, we build our original baseband signal ST. We start from 0. They use a loop to multiple single-tone cosine waves, each with its own amplitude and frequency. By summing them up, we successfully create a complex multi-frequency real signal as our processing input. Next comes the Hilbert transform. Here is a critical MATLAB trap. The built-in Hilbert function does not directly return the Hilbert transformed result. Instead, it outputs an analytic signal. The real part of this output is our original signal, and only the imaginary part is the true Hilbert transform we need. That's why we add the extra step to extract the imaginary component. This method is widely used in communication systems, envelope detection, instantaneous frequency calculation, and many advanced signal processing applications. Okay, thank you for your attention. Next part.
On this slide, I will cover the core formulas for generating the upper sideband and the lower sideband. First, the theoretical foundation is the phase shift method. The two key equations are shown on the left. On this part, in MATLAB, we generated the auxiliary carrier sin C and the cosine C. Then we apply this formula directly to create the x upper sideband and the x lower sideband. On the left, on the right, we will use the FFT transform. Finally, we perform the FFT transform with the MATLAB code with FFT shift and normalize the frequency axis to fs to minus fs to fs, clearly showing that the spectrum shift and the
single sideband characteristics.
This section is a continuation of the previous part. You can see the first figure. This is the amplitude spectrum of the real signal. The second figure, you can see that the valid signal lies outside the cutoff frequency. The third figure, you can see that the valid signal lies within the cutoff frequency.
Then I will introduce the Simulink method to realize the task. And this is the overview frame of the Simulink. You can see that in the left side there are three singleton signal, and we find the sum of them, and then we transform this into analytic signal with the analytic module, and we get the real part of it and the imaginary part of it. The imaginary part of it is just the Hilbert transform of the signal. And we multiply the real part of it with the carrier signal cosine and get the USB and multiply it with the sine signal. By using the cosine signal subtract the sine signal, we get the USB signal, and by find the sum of the two signal, we get the LSD signal. And here's the signal parameters, and you can see that the sample time is 0.00005, and so the sample rate is just the same as the script. It's 20,000, and you can see that the frequency is respectively 1,000 pi, 2,000 pi, and 3,000 pi. So actually the frequency is 500, 1,000, and 1,500, just the same as the script. And the amplitude is also the same, respectively 0.5 and 0.3. And the carrier parameters, we can see both the frequency are 8,000 and the amplitude are 1. And to generate the cosine signal, we can give it a phase bias by 0.5 pi. This is the result of the Simulink, and you can see that the amplitude spectrum of the real signal in this plot, and the left side would be the USB signal, and the right side would be the LSD signal. And this is the spectrum of the USB signal. You can see that both the effective signal are outside of the carrier frequency. Also, this is the spectrum of the LSD signal. You can see that the effective signals are inside the carrier frequency, which is proper. And finally, we can actually generate code by this function, and just as we show in this video. And however, the code is just by C code, but you can directly use the part the next time. And here's our presentation. Thanks.
Okay, so it was good, very good. Thanks, Carl and Ziegler and the other group members. Yeah, so that's what I want you to present. That's how you present, okay? Keep in mind that's how Carl and his group present. So every student should present like this, not only one or two. So yeah, and that's how you get the very good points in presentation, right, and the project. So as a whole, they perform very well. Thanks and good. So next time we will have a longer presentation. So we have some time. So let's try to finish our course then. Okay, let's finish our course. So I'll start again. We'll do some, so here, yeah, okay, so we were here, yeah, so you can get this, the output of the LFSR, which is here, so you can get that using, well, I was making it over here, so how you can make, so here you can get F, and here it is N, and then you have X of N minus 2, and then you have X of N minus 2, and finally you have this resistor X of N, right, and here you write down resistor, right, so starting from like 0, 1, 2, and 7, right, so here the first step starting with 1, 0, X of N minus 1 is 1, and here we got 0, and this 1 modulus, so we got 0 to 1. Similarly for 1, you have 0, you have 0, you have 0, plus 0, so we got this, we got 0, right, and similarly go on. So, and you have the initial states here. The initial states are given, right? X of n is equal to X of n minus 2 is 0, X of n minus 1 is 0, and X of n minus 2 is 0. So you are given those states, you build those, right? You start from here, starting from 0, you get X of n minus 2, X of n minus 2, X of n. So what are those? So X of n minus 2 is 0, X of n minus 3 is 1. So what is your X of n? X of n is basically is equal to X of n minus 2 plus X of n minus 2 equal to 0. You get to 1, so 0, 0, and then 1. And similarly for X of 1, X of 1, here you have X of n minus 1, right, that is 0. X of n minus 2 is also 0, so you got 0. And so on, right? If you do that, if you go for several times, what you got? You got 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, and so on. So this sequence is periodic with period 7. This sequence is periodic with period 7. Now, here, what is a frame synchronous scrambler? In a frame synchronous scrambler, the output of a PN sequence generator X of n, here X of n is X of n, the output sequence X generator X of n is XORed, XOR, XORed bit by bit with the user's data stream Dn to generate the scramble bit sequence C of n. That is, so C of n is basically equal to D of n, which is the generator, which is the data, for user data, and this X of n, which is basically the Cn generator, right? So here you will get, here is that scrambler, and here is that descrambler, right? Scrambler and descrambler. So here you have the user bit data, BI, and you have this X of I, which is PN sequence generator data. So here, and then you got CI, all right, and then you transmit it at the descrambler. Again, you have this CI, which is the combination of DN and XN here, right? It is feeding here, adding. So here is the PN sequence generator, same, well, both are same, right? Both are similar. So here at the descrambler, the user data is recovered by adding the output of identical PN here, adding identical PN generator to the scramble bit stream C, and here to the scramble bit Cn, and you get the output, which is basically Cn plus this modulator x of n, and we know what is x of n, so just place that x of n. These two will cancel, so we get Pn. So we get Pn. Now what is the synchronous network? What is SON, synchronous optical network? Is a digital data transmission standard for telecommunication infrastructure network in North America and Japan. Well, the SONET standard requires that all user data be scrambled by the output of a CN sequence generator specified by a generator polynomial of this 1, this modular D6 plus, this modular D7. So here we have the SONET data, and here is that 7, right? You could see the state. This is SONET data. This is the scramble. This is that x of n, right, or x of I. So here you combine all of those with the data, you get the scramble SONET data. You get the scramble SONET data. Here R is 7. It's a 7 shift register, right? It's a 7 shift register. So the maximum period in this case would be how much? Maximum period or PN sequence would be how much? PN sequence in it would be. So here, how much would be the PN sequence? And the the PN sequence, this would be, this would be 127. PN sequence. And then self-synchronous scrambler. In a self-synchronous scrambler, the input bit stream is added directly to the input of an LFSR. The LFSR input Cn is also the scramble's output. So here, C of n is basically the user's data, and plus this C of LFSR is also the scramble's output. So this is the scramble's output. Note that the scramble form a feedback shift register. So it's a form a feedback shift register. Now the D-scrambler on the other hand consists of a feed forward shift register. So one is feedback, one is feed forward. The D-scrambler output is obtained by XORing the scrambled input Cn with the output of the LFSR. So this is basically the D-scrambler output, which is Cn, and this modulo 2 summation, which is equal to here, and this will cancel out. So you got what you got. You got this CFN. This is the property, right? This will cancel out with this. So you got CFN. And here is that scrambler and D-scrambler. So one is feed forward, one is feedback, and here is the feed forward. So D-scrambler, this is D-scrambler, and this is the D-scrambler. Example, a sequence G of n is given as this. Is input to a self-synchronous scrambler. Assume that the LFSR is defined by degree 5 polynomial, 45 octal from table 9.4. Scratch the scrambler. Assume that the initial state of the shift register is set to all zeros. Determine the scrambler sequence. So it is it is 4, 5. So what is the digital format of 4 and 5? 101, 100 and 101, right? So combine them. So if you combine them, what you get of G of t? If you combine here, we have 45, right? So we have 45, 8. So we can write down what is 4 is 100 and 5 is 101. So if you combine that, you got 100, 1. So if I want to do this G of t, that G of t is equal to T5 plus T5. Right? That's what would be my. Now we need to sketch the scrambler here. So here is that scrambler, right? So we can write down what this is G5. This is G5. Right? And this one, right? G4, G3, G2, G1, and J0. Right. So here is that self-synchronous scrambler example. So we can build like this, right? So this is how we can. We want to implement this, right? These 5, these 3, and 1. That's how we build, right? That's how we build. So here you have user data, and then you have the scrambled data here. And you have user data, and that you have the scrambled data, and scrambled data basically that Cn is what? Cn here is Cn, and this over there is n minus 2, and this over here is 5. That would be the scrambled data, right? And here, so this is what the, and assuming now, assuming that the initial state of the system is set to all zeros. So all zeros, so you start with all zeros, right? So that means C minus 1, C minus 2, C minus 3, C minus 4, C minus 5, all are zeros, right? All the C's are zeros. C minus 1, N minus 1, C, N minus 2, C, N minus 3, they are all zero. So now the input sequence is given here. This is the input sequence. So there are 12 bits input sequence, right? Bn are from 0 to 12. Bn. They are from 0 to 12, right? Okay. For n, this is for 0 to 12, and n 12. And here is 0 to 12. So here is right? And it's from 0 to 12. If you read here in the data, it is given 1 0 0 0 0 0. If you add, if you count, there will be 4. Now here is a sketch, and now here the scrambled data, right? The scrambled data output is given by this equation, right? Cfn plus Cfn minus 2, and this plus modulo Cn minus 5, and now we can, here this table, we can write down our data in table like this. We have data, and then we have this shift register, and then we have this scramble data, right? So let's start with n is equal to 1. So what would be our C? Let's start with C. Well, let's start with n is equal to 0, right? N is equal to 0, and B1, B0 is 1, right? So here is here, right? So B0 is 1. Now let's start. Let's see if n is equal to 1. If n is equal to 1, B1 is 0. So B1 is 0 here. Here B1 is 0, right? And then we got 0. Let's say n is equal to 2. So B2 is 0. N is equal to 2. B2 is 0. What would be my C0? C0 is 1. Right. Similarly, C1. What is C1? C1 is also 0. What about C3 and 4 and 5 and go on, right? So if you go on doing all that, you will construct table like this, right? You will construct table like this. This is our Tn, and this is our Tn minus 1, Tn minus 2, Tn minus 3, n minus 4, Tn minus 5. Right. So sample bit. So here T of n would be just you can get when you put n is equal to, let's say 0, right? You get B1 of we know what is B0. B0 is 1 here. Similarly, B1 is 0, B2 is 0, B3 is also 0, and so on, right? So they are, if you see here, Tn, they are all Tn. And then the scramble data, Cn, you see here, you can construct that if you put on all the values, right? So you will get all those values here, right? All those scrambled values here. Now, ATM scrambler, asynchronous, what is ATM scrambler? Asynchronous transfer mode technology. Well, it is widely deployed to transport internet traffic in the form of data packets. The user data is scrambled by a self-synchronous scrambler whose LFSR is described by this polynomial 1 plus P43. Well, P raised to the power 43. So here is the user data. Here is the scrambled data output 1. We have this 43 shift register. So this is Cn, right? So this is user data. This is Cn. We got the scrambled data. This is here. This is scrambler. What about the B-scrambler? We have scrambled data, and then we have this 43-bit shift register. Here we get the scrambled data. This is B-scrambler. Now the bandwidth of a digital baseband signal. The bandwidth of a digital modulated baseband signal is defined as the width of the frequency band from DC to a frequency D. Well, we know that, which contains significant spectral components to represent the signal with acceptable distortion. The definition implies that spectral components to be included in the signal are determined by its relevance in a given application. Thus, there are many definitions of bandwidth depending on the context. The first is half power bandwidth, 3 dB, right? So frequency where the spectral density main lobe drops to 1/2 of the peak value, that is 3 dB below. That is called the half power bandwidth. Half power bandwidth. So here is the right. Well, this is that 3 dB, right? This is that 3 dB. So this is the power spectral density here, right? And this one below, this one is basically the null bandwidth, and this is the 3 dB bandwidth or half power bandwidth. Then first null bandwidth. What is that? First null bandwidth is width of the main lobe of the spectral density function, where most of the signal power resides. For the main lobe, right? The first lobe, the main lobe. We're talking about that. The width of the main lobe spectral density, a function where most of the signal power resides. Very popular measure of the bandwidth for digital baseband